Hi friends, let's review for our quest. First we've got to solve. What do we want to do? We want to set this equal to 0 and factor. So let's bring over negative 15. So 2x cubed plus 3x squared plus 10x plus 15 equals 0. 1, 2, 3, 4. Let's split this down the middle and factor by grouping. So take out an x squared. That's 2x plus 3. Remember to bring this sign down. Plus, bring out the 5, and we get 2x plus 3 equals 0. Notice we've got like factors here. That is our new greatest common factor. Bring it to the front. So 2x plus 3 times x squared plus 5 equals 0. Next, set each factor equal to 0. So that is going to be 2x plus 3 equals 0. So x equals negative 3 halves. That is our one real solution. Next, x squared plus 5 equals 0. X squared equals negative 5, square root, x equals plus or minus I root 5. So this is our two imaginary solutions. So we've got one real, two imaginary, fulfilling our need for 3 solutions. So our solution set is negative 3 halves and plus or minus I root 5. There we go. So next we're moving into the inequalities, where we are going to, same thing, set equal to 0. In this case, greater than 0, and then factor. So x cubed plus 2x squared minus 3x is greater than 0. We're going to factor because we are looking for our restricted values, or critical values in this case. So let's take out the x, and we get x squared plus 2x minus 3. Factor again, that's x plus 3 times x minus 1, giving us 1, 2, 3 critical values here. So x equals 0, x equals negative 3, and x equals positive 1. We're going to put those on our number line. So 1, 0, negative 3, and then we're going to do some test values. Remember, this is strictly greater than, so it's going to be open, open, and open. So here goes. Let's do one way down on the left. We'll do negative 10. And when we're doing this, we can just go right to the factors here because we have not changed the value of this inequality at all. It's just in factored form. So we're just kind of looking for signs here. So it's going to be a negative 10, and then negative 10 plus 3 is negative, negative 10 minus 1 is negative. A negative times a negative times a negative is a negative. Is that greater than 0? No. So we will not shade this interval. Let's plug in a negative 1. A negative 1 will be a negative, or a negative 1, and then that'll be a positive, and negative 1 minus 1 is a negative. So we end up with a negative times a positive. That is a positive, so that's true. So we will shade that interval. And then if we choose one in between here, probably not going to work, just saying, but we'll give it a shot. If we put in 1/2, so that's going to be a positive, and a negative. So if we have a positive times a negative, that's a negative. That is not greater than 0. So I was pretty sure that that interval wasn't going to work. Let's try positive 10. That's a positive times a positive, which of course is greater than 0, which is why we will shade that interval. So just testing. You got to do test values when you have an inequality. So finally, let's do our interval notation here. Parenthesis, negative 3 to 0, union, parenthesis, 1 to infinity. So this is our number line. This is our interval notation. Got another one of those that's a little more challenging. So here's number 3, solve and graph once again. So right away, we see this x plus 2 on the bottom. Now remember, this isn't a rational inequality here. Root word of rational, ratio, so fraction. So right away, x cannot equal -2. That is going to be a critical value on our number line. And because it cannot be equal to -2, we will put an open circle even though it's got the or equal to right there. Why? Because it is restricted. Okay, so we've got that critical value out of the way. Next, let's cross multiply and solve this inequality. So 3x minus 1 is less than or equal to 4 times x plus 2. 3x minus 1 is less than or equal to 4x plus 8. So minus 3x minus 8 gives us -9 less than or equal to 1x, which logically means the same thing as x is greater than or equal to -9. So -9 is our other critical value, which we'll put right there. But this time it says x could be equal to -9. So this one is solid. So this is giving us 1, 2, 3 intervals to test here. So let's test -10 and let's see what happens. So whenever we have a rational inequality, we make sure to go back to the very beginning of the problem when we do our test values. So let x be -10. So 3 times -10 is -30. -30 minus 1 is -31. -10 plus 2 is -8. So this is positive. And is it less than or equal to 4? Well, 31 divided by 8 has to be a little bit smaller than 4 because 32 divided by 8 is 4. So it looks to me like we indeed have a true statement here. All right, let's put something in the middle here. Let's go with -5. So let x equal -5. If we put in -5, we get -15 minus 1, that's -16, over -15 plus 2 is -3. Is that less than or equal to 4? Well, 3, first of all, negative over negative, positive, and then 3 goes into 16, that's 5 1/3. Is 5 1/3 less than 4? No. So first one true, second one false. If it's false, we do not shade. Next, 0. Thankfully, something easy to plug in here. So let x equal 0. That means cancels out the 3x, cancels out the x. We end up with -1/2 is less than or equal to 4. This is true. Hooray. There's our other interval. So, which makes sense. So now, this is our number line. We have graphed it. Our interval notation will be -infinity to -9 bracket union 2 to infinity. So remember, we're solving and graphing. Once again, why do we have a restricted value that is open? Because this is a rational inequality. Okay, moving on to asymptotes, holes, and finding the domain. So once again, these are rational inequalities. Rational functions, my bad. When we have a rational function, remember what the fraction bar represents. The fraction bar represents division. So think of these as division problems. If you have no clue what to do, then perform the long division. Now, one thing I do see here is that I see some expressions that can be factored. Factors of -4 that add up to -3 are going to be x minus 4 and x plus 1. When we move to the bottom here, we've got x squared minus x minus 6. That is going to be x minus 3 times x plus 2. So we do need to factor here because one thing we're looking for is we will have a hole, or better known as a point of discontinuity, if one of these factors cancels. Well, nothing cancels. So what does that mean? Well, A, it means there's no hole, and B, it means we can very clearly see that there are vertical asymptotes because we have two restricted values here. So vertical asymptote at x equals 3 and x equals -2. Remember, if you don't put x equals, it's wrong. We're not just talking about values. We're talking about vertical lines, so they need to be described appropriately. Let's go after horizontal asymptotes next. Now, here's what I know. I've got a like degree on the top and the bottom, and this goes back to the whole idea of division. If we actually perform the division, it will give us a quotient, and that quotient is the horizontal asymptote. So I'm going to put this right underneath. The quotient of the division problem is the horizontal asymptote. So when we perform this, x squared goes into x squared plus 1 time. 1 times x squared is x squared minus x minus 6. Draw the line, change the signs, cancel. We end up with -2x plus 2. If I subtracted right, that looks right. So think about what we actually just did here. So here it is in factored form. If we write it as essentially a mixed number, what we end up with is -2x plus 2 over x squared minus x minus 6 plus 1. That 1 is the quotient. And like we have seen in class, whenever we have a constant value that is just added on to the end of the function, that creates a vertical shift. And that vertical shift is where the horizontal asymptote is. So our horizontal asymptote is at y equals +1. Now, we will learn, actually, it's a little bit more advanced algebra, but we learn what to do with that quotient a little bit later in the course. So what do we have here? We got 2 vertical asymptotes. We got a horizontal asymptote. And remember, the domain and the vertical asymptotes kind of go hand in hand here. So our domain is everything but 3 and -2. So -infinity to -2 union -2 to +3 union 3 to infinity. Very busy problem, but once again, a reminder, the horizontal asymptote is the quotient. Not the remainder, just the quotient. Let's do it again with number 5. So, different situation here, because now the degree of our numerator is greater than that of our denominator. But once again, this is a rational function. So a rational function is begging for you to do division. So let's go ahead and do the division. -2x cubed plus 0x squared plus 0x plus 0. This is just one term, so I got to add on a whole bunch of zeros to actually make the division happen. I'm also missing a power of x here in the divisor. So x squared plus 0x plus 1. Let's do the division. X squared goes into -2x cubed, -2x times. -2x times x squared, -2x cubed, -2x times 0, plus 0x squared, plus or minus, it doesn't matter, it's 0. -2x times 1, -2x. Draw the line, change the signs, cancel, cancel, 2x plus 0. And then, of course, x squared will not go into 2x, so this is your remainder. So what we see here, once again, is we have a quotient of -2x. Now, notice it's not just a constant like it was in the previous problem. So remember, our quotient in the previous problem was the horizontal asymptote. And it was horizontal because it was a whole number. But if our quotient, brief technical difficulty, once again, if our quotient is not a whole number, if we think of it in the form of y equals mx plus b, this is a slant asymptote. So not a horizontal, but a slant at y equals -2x. And how do I know I'm going to have a slant? Because my degree of my numerator is just one bigger, only one bigger. The degree of the numerator is one bigger. That will always yield a slant asymptote. Now, we can finish this problem off by looking at the denominator of the rational function and noticing that we have x squared plus 1. If it's x squared plus 1, no real number will ever make this go to 0. Therefore, our domain is unlimited. There are no vertical asymptotes. The domain is all real numbers. So this would be a continuous function with a slant asymptote. Let's keep going. Number 6, still looking for asymptotes, still looking for holes. So I see something that can be factored. Let's give it a shot. So that is x plus 3 times x plus 1. And when I see x plus 3 squared on the bottom, I see that something is about to cancel. Hooray! If something cancels, which it will, that is when you create a hole. Remember, a hole is the same thing as a point of discontinuity. So, right away, I know that my domain is going to be restricted here. So, this is a little bit tricky because we've got something that's canceling as well as that factor is repeating itself. If that factor is repeating itself, it kind of supersedes the whole idea of a hole, and we just have a vertical asymptote there. So vertical asymptote at x equals -3. If this would have been a different factor, then it wouldn't have just been an asymptote, it would have also been a hole. So maybe I'll have to do a whole other video just on that. So this is what we do call the simplified function. So the function simplifies to x plus 1 over x plus 3. And now do we have a horizontal asymptote? Yes, we have a horizontal asymptote. So once again, if we do the division, and you could do the division from here or you can do it from here, but very quickly we see that x plus 1 divided by x plus 3, it just goes one time. Remember, we only want the quotient. So the horizontal asymptote is 1. Horizontal asymptote is 1. Domain, everything but -3, negative infinity to -3, union, -3 to infinity. And once again, how come our hole went away? Well, it's because we had a repetitive factor there. I'm going to do a problem on another video that just tells you how to find the hole. Okay, lastly, f of x equals x minus 5 over 4x squared minus 9. Can we factor this denominator? Yes, we can. X minus 5 over 2x minus 3 times 2x plus 3. Nothing cancels. So we do have two vertical asymptotes. Vertical asymptote at positive 3 over 2 and a vertical asymptote at -3 over 2. But this time, do we have a horizontal asymptote? Yes, we do. If we do the division, we see x minus 5 divided by 4x squared plus 0x minus 9. So here's the question. Does 4x squared go into x? No. Well, how would you say that? 0 times. So 0 is the quotient. The horizontal asymptote is y equals 0. Just a reminder, if your degree of your numerator is less than that of your denominator, you will have a horizontal asymptote of 0 every single time. Lastly, let's find that domain. That domain is negative infinity to -3 halves, union -3 halves to positive 3 halves, union 3 halves to infinity. Asymptotes and domain. Next, we're graphing. So here we've got a factored function. Hooray, it's already factored for you. Let's just very simply, not a lot of precision necessary here, graph this given function. So first of all, if it's factored, set each factor equal to 0. So -2x cubed equals 0. That yields a triple root of 0. So x equals 0, and that is multiplicity of 3. Next, 2x minus 6 squared. So if we've got 2x minus 6 squared equals 0, square root, we end up with 2x minus 6 equals 0, plus 6, 2x equals 6, x equals 3 as a double root. So 3 is a double root, so multiplicity 2. And then finally, we got a happy little x plus 4. X plus 4 equals 0, x equals negative 4. That's a single root of negative 4. So here are our roots and their multiplicities. Remember, if the multiplicity is odd, either one of those, it will pass. If it is even, it will bounce. So I've got our x-axis numbered here. 1, 2, 3, 4. We've got a point there. It is going to pass. At 0, it is going to pass. And at 1, 2, 3, it is going to bounce. Now, what's the degree of our function? It is 1, 2, 3, 4, 5, 6. And our leading coefficient is negative. So if it has an even degree and a negative leading coefficient, then the end behavior is going to be down and down. So down and down. So here we go, down and down. So once again, we're passing, we're bouncing. So we are going to pass, we are going to pass, and we are going to bounce. There we go. Remember, I'm not going crazy over precision here. I don't really need to know a relative max or relative min. I'm looking for behavior on the x-axis and end behavior as well. Very simple to graph there. Next, at the top, negative 2 times x plus 3 squared plus 8. We have talked at length about this in class. This is a quadratic expression, a quadratic function. Its graph is a parabola, and this is even in vertex form. So we've got a vertex at negative 3, 8, and it is going to open down, and it is going to be tall and skinny because that a value is negative 2. So back 3, up 8, 1, 2, 3, 4, 5, 6, 7, 8. Squish it right there. Now, a value is negative 2. Think about what that does to the graph. Instead of going over 1, down 1, we're going to go over 1, down 2. Back 1, down 2. Instead of going over 2, down 4, we're going to go over 2, down 8. Over 2, down 8. 1, 2, 3, 4, 5, 6, 7, 8. Remember, I'll go ahead and put in our axis of symmetry so we can see it a little bit better here. So 1, 2, 1, 2. We got 5 points. Let's graph this guy. There we go. Everybody should be able to quickly and easily graph a parabola at